All right, our next speaker is George Brimhall. George is co-founder and managing member of Clementine Exploration, which since 2011 searches for porphyry copper deposits in the Greater Butte Mining District. His PhD research on the Butte pre-mine stage mineralization. In 1972, he became a Stewart Mine Geology for the Anaconda Company. After working for the Anaconda Company, he was a professor of geology at Johns Hopkins University and then the University of California, Berkeley for 32 years. Everybody, please welcome George.
Thank you, Mike. Also want to thank all of you for being the hardcore people who stay here on the last day. That's really appreciated. I want to acknowledge the abiding support of my colleagues in Clementine that are listed, and also acknowledge scientific staff members of the U.S. Forest Service that I've worked closely with on permitting and compliance, and also in the DEQ, and scientists within the U.S. Geological Survey. Okay, the problem I'm going to talk about is actually kind of scary. It's a discovery gap, and it's shown on the diagram to the right, which is the distance between the number of known greenfields discoveries on this side and the price of copper on that side. And that's a remarkable gap. You'd think that companies charged with finding copper resources would be more successful than that. But we all have a lot of blame in this for not continuing to advance our understanding of porphyry systems and the models that guide us. So that's a 20-year decline in economic copper discoveries, and corporate acquisitions don't solve this problem. What I'm going to address today, I hope, will be an impactful solution to guide deep exploration. The easy deposits were outcropping, and those are gone now. So the job of the exploration geologist is much tougher. And what I'm going to show you is based on modern digital mapping, GPS guided observations on the field, and also on petrology, mineral chemistry, and thermodynamics, 3 areas that, if done correctly, really offer some new insights. I challenge the focus on ore deposits as giant geochemical anomalies because that admits a key dimension. Porphyry copper deposits are also energetic magmatic hydrothermal systems, and their time-integrated thermal flux determines their size, that is, their tonnage. How energetic are they? If they're not contained, they erupt and form a Mount Pinatubo type mega stratovolcano with oxidized sulfur occurring as anhydrite. And that literally influences the chemistry of the atmosphere, the heat flux coming into our planet. So they're magnificent examples of volcanic eruptions, but when they don't erupt, I argue those are world-class porphyry copper deposits. What I also do here is convert the porphyry copper model, which was a very hard-earned picture published by Gustafson and Hunt and Lowell and Gilbert, from a picture to the first operational quantitative model based on hydrogen convection, which is something that's been overlooked largely. Assays alone are no longer the gold standard to rank prospects. And if you're interested, I have a publication here that you can access just by scanning that QR code to see the basis for what I'm going to talk about now. Well, let's talk some geology now. The color map is an APG lithotectonic base map, and you can see Butte is a large red circle to the northwest, and directly south of that is Bingham. And those are the 2 main deposits I'm going to talk about today, both world-class porphyry copper systems. Our work is focused in the Greater Butte District in this belt here. Our main prospect is Clementine, shown as a small red dot there, but that belt continues to the south through the Pioneers, through Quartz Hill, Canavan Gulch, which is a Molly porphyry, Hecla, Argenta, and finally Bannock, which was the first frontier capital in Montana. And the main thing to keep in mind is the structural environment here, where this is a severe age thrust. There's a north-south striking anticlinorium coming down in the hanging wall of the severe age thrust. And in that frontal anticline, all of these deposits are located on domes. They're almost like oil fields, places where magma's ascended. And we got very interested in what causes that clustering. And my colleague in Clementine, Bruce Marsh, who's an expert on the separation of features by instabilities, showed that the spacing that I pointed out to him were actually Rayleigh-Taylor instabilities of magmas hitting that frontal thrust and then separating like fingers coming up. If you ever swirled a glass of red wine, you get little fingers that come down with equal spacing. Same feature. Those are Rayleigh-Taylor gravitational instabilities. The main feature I'm going to point out is something new. It's a rock with little orbs in it about the size of your fingernail with actinolite in it, and we call that orbicular actinolite. That was first noted by two of my former Anaconda colleagues, Bill Atkinson and Mark Inaudi, in drill core at Bingham, and published in 1978. This map shows the global data for porphyry copper deposits as compiled by the USGS. And on the right-hand side are tier 1 giant porphyry copper systems that are economic. Those are tier 1. Tier 2 are mainly economic, but as you come over here to the left side, those are sub-economic or uneconomic systems. The main porphyries, Bingham is located here, Butte's in there. The largest porphyry copper system operating in the world today is Escondida, which is in here somewhere. And that line shows the in situ dollar value of those tier 1 systems. It's about $1 trillion at $4.50 a pound copper. It's about the value of a giant oil field. So these are enormous copper resources. Some of these porphyries over here have this orbicular actinolite alteration. And my friend Mark Inaudi was kind enough to share his information with me. Not all tier 1s have that alteration. Some don't, but they're still big. There's one data point down here with that alteration, which is Battle Mountain in Nevada. I would argue that needs more drilling. But that's an incredible association of that alteration with tier 1 systems. Why don't they get any bigger than that? Why is there no T0? I think we can explain that as we go along. Those are the systems that have so much energy they erupt and make a Mount Pinatubo volcanic eruption. Now, why would I want to share this information? Because it's a competitive world. I do it because we need to acknowledge things bigger than ourselves. We have a major challenge facing our country, which is to find these earth resources. In fact, the demand for green technology now is to find the equivalent of 16 Escondidas. There's plenty of room for everybody in this room to take part in that. And I would sincerely hope that some of you would pick up that challenge. This is some of our mapping along our Clementine prospect. These orb zones are shown with these circles. They're on the left side of the anticline. That's the top of the dome. There's orbs on the east side here. And it's interesting that springs shown with these blue circles are exclusively associated with those orb zones. If we blow this zone up into the middle panel, you can see in red a system of vein Gaussins that I mapped, and these had never been hit with a rock hammer. You could just see nobody had ever been out there. It was a very under-prospected area, and we found 2 new plutons on here. We could date the sphene and zircon in them. Got about a 71 million year date on the sphene, which is the same as our date on sphene in the actinolite zone. And then by looking at multi-element chemistry of the vein systems here, where the system is most highly enriched in tellurium, the selenium, bismuth, and so on down along here. The orbs have exactly the same ranking. So it's the same fluid making these veins as makes the orbs. I noticed two kinds of breccias. All these veins are vein breccias, like the early main stage in Butte. They're mineralized fault, basically, with breccia fragments in them. There's another type of breccia I don't understand yet. It's a matrix-supported clastic breccia that occurs, rocks in this huge elliptical pink zone. I don't know the origin of those yet. We hope to illuminate that with drilling. Now, how can we image these different tiers from tier 4 all the way up to tier 1? If we look at tier 1, this is the average size. It's about 1 kilometer from left to right on the diameter of the ore zone, and tier 4 is about 200 meters. So they're much smaller systems. So we're looking for tier 1 economic systems. They're the only ones that have this halo around the edges of this actinolite orb alteration. The reason it's there is because of time, that only in a really big system does the convection cell spread out and have a quasi-static system before retrograde cooling. So it's that long period out here where diffusion can operate. And I'll show you in a thin section why diffusion is so important. And following that, there's a retrograde collapse. This is the way we see the convective system, magma in air heating up, densifying as it cools, and then circulating around and around. So it's that stationary thermal maximum where hydrogen, which is the gas escaping from the top of the plutons that is new in our model, causes hydrogen embrittlement, same way it does in steels, and that gives rise to the high permeability that allows springs today to still be accessing through-going permeability. And the tier 1 we see is a Goldilocks size. It's not big enough to erupt, nor so small as to not develop the orbs. It's just the right size. And the springs today, shown in blue, represent continuous permeability since 71 million years ago. And surface water is accessing that permeability. This is what a thin section looks like now. Here's an orb. They all have little cracks coming into them. Ordinarily, advection would be in this direction. Diffusion would be perpendicular to it. So you get these planar alteration envelopes like in Butte zones. But at a cracked tip, this wraps around and grows bigger and bigger over time by diffusion. So that's why diffusion is such an important mass transport phenomena here. One of the lessons I've learned is as I mapped these actinolite zones, I didn't know what they were. I just mapped them as propylitic alteration, not knowing any better. But because of my training, I was trained to map even what we don't understand. And another way of saying that is to dignify our ignorance. Rather than dismiss it, celebrate it. And I saw over time those little red lines started connecting. And all of a sudden I realized they were actually a vein system. With that said, let's jump into a little bit of thermodynamics. This is a new phase diagram. This is log of the fugacity or activity of hydrogen getting lower going up, higher going down. So this is reducing, that's oxidizing. This is temperature increasing here from about 700 degrees, cooling over there. And the first thing is this brown zone is where titanite or sphene exists. The pink zone above is where anhydrite occurs. And so that's a boundary between anhydrite and titanite. That's exactly where the early stage Butte mineral assemblage is, pyrite, chalcopyrite, in contrast to Bingham, which has bornite in it. And that tells us right away there's two major types of porphyry systems we can show on here. And then the equilibria where actinolite forms is along here. It's under very reducing conditions down here that we get that actinolite. And then if we look at Mount Pinatubo pumices, they often have both anhydrite and titanite. So they're right on that boundary. And then if we now realize that the redox state of Mount Pinatubo is just like the fluids that make the early butte system, we see that connection between volcanism and these deep systems. Bingham early stage is up here, and where bornite chalcopyrite coexist. And a critical thing is the chemistry of the biotite. So this purple line represents the potassic zone in butte. Magnesium-rich biotite and magnetite potassium feldspar cooling from the fluids coming out of the magma where hydrogen is streaming, and then basically moving over here when it gets into the hematite field, like a right lateral fault, then cooling up in there. Now, there's another type of biotite in butte, which is related to the granite, the butte granite, and it's what you see in thin section is this dark reddish brown high titanium biotite that's much more reduced than the potassic alteration biotites. And that acts like a buffer itself, but with a different redox state. What that does in cross-section, this is a potassic zone. The early stage in butte has a thin propylitic zone on it, but what it means is there's fresh granite above that. If you went up Main Street above the Stewart, you could drill a 3,000-foot vertical hole through absolutely fresh granite before you saw the top of a porphyry system. It takes a very bold explorer to do that, and the big companies are risk-averse. They don't do that, but that's the kind of target that if you're in a granite system, you expect to find. The role of hydrogen is determined by computational modeling. That's our chemical space. And thermodynamics allows us to actually image hydrogen. Even though it's fugitive and long gone, we can resurrect its levels, from the mineral assemblage. The arc magmas in here are shown, as well as the evolved fluid compositions. And there's a magnetite hematite field, arc magmas here. We know porphyries are much more oxidized than a typical arc magma. And if we then complete this by adding in the cooling trend in the potassic zone, the wall rock buffer on a butte granite system, we can get a quantitative understanding of how this new model actually works. Without doing parametric modeling, we're not doing fluid flow modeling. We're letting the rocks tell us what the story is. And I do this by using a program SNOS by Jeff Dick, and compute the thermodynamic properties in the equilibrium constants from that. Okay, so here's the model that I mentioned. If we look at tier 4, 3, 2, and up to 2, we know those are like bagel-like convective systems, and their flow paths just circulate inside this green rock sort of propylitic alteration. They don't oxidize enough to get up to bornite. They don't get reduced enough to make orbs. But when we finally get to tier 1, we finally get to tier 1, the hydrogen comes out of the top of the magma, starts to ascend, makes potassic alteration with bornite. It cools, it goes to the distal cooling end, reaches where it makes actinolite orbs and graphite. And then a remarkable thing happens. There's a feedback in there whereby in tier 1 systems, hydrogen converts to water by oxidation with CO2 reduction to graphite. And that scrubs the copper out of the magma, very efficiently taking the copper out of the parent magma. And then the copper returns into the melt. And so it's the extraction of hydrogen out of the top and the return of hydrogen to the bottom of the system that makes the orbs, and then the conversion of hydrogen into water that keeps the system pumping copper out of the system. Now, if we look at a butte system, which instead of intruding sedimentary wall rocks like Bingham or Clementine prospect, if it intrudes a butte granite, you get a convective system inside of this much bigger one, because the granite buffer of the wall rock just keeps it from either oxidizing enough to get up to bornite or reducing enough to make the actinolite orbs. So it's a much smaller convective system. It'll make some really high-grade chalcocite and cobalt with advanced argillic alteration, but it's a much smaller convective system than we see with the Bingham type systems. Then if a system evolves to an even larger size, you can approach this eruptive threshold. And if that's attained, the system fails and explodes on the surface, and that's a Mount Pinatubo-like eruption. So in closing, what we've done in cross-section here is add an outer ring to the porphyry copper model, this bright green zone. That's this actinolite orb zone shown with that kind of a texture. It's a distal downflow zone, and in plan view, it's an outer ring on a bullseye target. And so what we do is what's called thermochemical exploration, not just assays, but with the heat. And that heat then gives us a whole other gauge at what the likely size of a target's to be. And hopefully we're looking for one right at the Goldilocks size, which is tier 1. Tier 1 systems are energetic enough to grow this special distal orb ring because of diffusion, but not so large that they erupt. But the challenges for us now is finding orb rings. That's one of our principal targeting features now, because they're indicators of tier 1 systems. We're not just doing random sampling, trying to collect enough data that typically one prospect out of 300, according to David Lowell, who was the best explorer that a lot of us have ever known. If you just try to randomly sample, you can drill a lot of holes and not find much. But if you're targeting now specifically areas with this indicator, you can fare much better. But it requires earning a social environmental license and acceptance deserving of operating permits, often in contested districts now. So there's going to be art and negotiations and a real effort to try to work with all stakeholders to do that. So I welcome questions.